Look at the sheer physical scale of the El Capitan supercomputer. The classical calculation would require 10 to the 32nd times the age of the universe to match what the photonic processor did in a fraction of a blink. This specific mathematical boundary terminates the noisy intermediate scale quantum, or NISQ, era. It provides undeniable, verifiable proof that quantum hardware can execute tasks permanently beyond the reach of classical parity. This photonic achievement is part of a broader hardware inflection point occurring across the global quantum ecosystem in 2026. Simultaneously, Google's Willow processor has demonstrated below-threshold quantum error correction in superconducting qubits, meaning the system mathematically suppresses errors as it scales up. These combined milestones establish a new industry consensus, achieving fault-tolerant quantum computing by the early 2030s. These hardware deployment timelines condense. They are reaching the critical cybersecurity deadlines that global enterprises must meet to protect their data. The window for treating quantum technology as a theoretical physics experiment has closed. The mandate has shifted to active structural integration. To understand why Juzang 4.0 matters, we have to look at the primary vulnerability of optical quantum systems, photon loss. As light travels across beam splitters and detectors, a fraction of the photons inevitably disappear. In 2024, researchers published a classical algorithm using a matrix product state, or MPS, method. It was designed as a direct theoretical threat to photonic advantage claims. This diagram shows the MPS algorithm. By exploiting points where photons leak from the optical circuit, the classical tensor network calculates the remaining degraded state. Tracking these states allowed MPS to simulate earlier Gaussian boson sampling outputs using standard supercomputers. This algorithm threatened the premise of photonic quantum supremacy by suggesting the outputs were effectively classical noise rather than quantum computation. Juzang 4.0 was engineered specifically as the physical countermeasure to defeat the classical MPS algorithm. The team redesigned the generation of input states, achieving a 92% efficiency rate that drastically minimizes initial photon loss before the computation even begins. They utilized 4 optical parametric oscillators to cleanly generate 1,024 squeezed states of light, creating a massive, dense influx of quantum information. This schematic maps spatial-temporal hybrid encoding. Instead of spreading photons physically, the system incorporates time intervals by looping them through delay circuits. Quantum information spreads across space and staggered time, routing 16 physical channels to access 8,176 effective quantum modes. Building a purely spatial optical circuit with over 8,000 modes would be an engineering impossibility due to hardware bloat and catastrophic photon loss. The hybrid approach bypasses this entirely. The empirical result of this architecture is the detection of 3,050 photons simultaneously in a single run. This extreme entanglement density pushes the system into a high photon regime that outpaces the bond dimensions of any MPS tensor network. It renders classical spoofing mathematically impossible and secures the advantage. While technically impressive, Gaussian boson sampling remains a specialized benchmark. It cannot run universal algorithms. However, Juzang's massive, low-loss squeezed light sources successfully enable the generation of these three-dimensional, highly entangled cluster states. These cluster states serve as the fuel for measurement-based quantum computing. This framework translates optical sampling into universal, fault-tolerant photonic computing. This photonic roadmap runs parallel to approaches like IBM's Starling system, which leverages specialized error-correcting codes to target 200 logical superconducting qubits by 2029. It also mirrors Microsoft's Majorana 1 topological core architecture, which aims for inherent stability right at the hardware level. Regardless of the underlying modality, whether photonic, superconducting, or topological, the cross-industry successes of 2026 lock in a definitive trajectory for utility-scale systems in the early 2030s. In the enterprise space, the operational reality is that quantum hardware will augment, not entirely replace, existing classical high-performance computing stacks. The immediate application lies in targeting highly specific bottlenecks amenable to quantum acceleration, such as modeling strongly correlated transition metal systems in battery chemistry. This flowchart outlines the requirement: quantum processing unit middleware. It acts as a central router, sending standard tasks to CPU and GPU clusters while routing the specific quantum problem to a QPU solver. Once executed, the middleware shuttles the resulting data back into the classical simulation for completion. Developing this integration capability requires building internal algorithm literacy and classical quantum pipelines, a process requiring 2 to 5 years of dedicated engineering. Organizations aiming to extract return on investment from the hardware projected for 2029 to 2031 must begin funding and architecting these hybrid workflows immediately. The ultimate endpoint of this rapid hardware scaling is the deployment of a crypto-analytically relevant quantum computer, or CRQC. A CRQC will systematically shatter the foundational algorithms of current asymmetric cryptography, completely compromising the RSA and ECC protocols. This inevitability drives the harvest now, decrypt later threat model, where adversaries are actively intercepting and storing encrypted enterprise and state data today. Because intercepted data is already compromised, security migration must be completed years before CRQC hardware actually comes online. The United States government has issued a regulatory response via the CNSA 2.0 directive for national security systems. The directive establishes hard deadlines. Legacy cryptography must be phased out entirely by 2030, with full post-quantum compliance mandatory by 2035. This is a global regulatory baseline. The European Commission has published parallel transition roadmaps demanding high-risk use cases implement post-quantum upgrades by default. Complying with these mandates requires an architectural framework called crypto agility, allowing organizations to swap out specific cryptographic algorithms without rebuilding their underlying applications. The mandatory first step for IT leaders today is executing a comprehensive crypto inventory to identify every vulnerability across their network. The 2026 hardware milestones establish quantum technology as a functional component of the enterprise engineering and cybersecurity deployment cycle.